Let's start with my counterexample.
Okay. Thank you, Avi, for the invitation. It's always nice to be here. Actually, I feel that I sample Princeton every few years, and last time I sampled it was when I got interested in these inverse theorems. Okay. Anyway, Ben in his talk mentioned this new, very recent inverse theorem for the Gowers norms when you look at the group Z mod NZ. So showing that if your function has a large UK norm, when the norms are defined in the group Z mod NZ, then that it correlates with these nice object called nil sequences. But I want to talk about a different story, or the story of a different group. So for this talk, we fix the group G, which is fp to the n. So we think of p as small, or so it's fixed, and n is large. Okay, so I think you in general, you can define the Gowers norms for any finite abelian group. I think Luca did that in his talk. And he asked similar questions. So let me start by doing that. So for this entire talk, the group G is fixed as fp to the n. Although the definitions hold for general finite abelian groups. So let me first start with repeating the definition of a discrete derivative. Okay, so take a function f from G to the unit disk. Then for, it's okay, it's too small. Then for any h and g, we can define the derivative, or multiplicative discrete derivative in direction h. This is f of x plus h, fx bar. Okay, so I don't know if maybe I won't try to bring it all the way up. Okay, so for example, if delta hf is 1, then f is constant, is some constant c in the unit circle. So it's right. So if I take h equals 0, then I see that f has to take values in the unit circle, and if it's the same for every h and g. Okay, if the derivative is constant is 1 for any h and g, then my function is constant. And say if I take two consecutive derivatives, so if I differentiate twice, if this is trivial, then for any h1, h2, and g, then f is necessarily a constant times a character. Okay, let me quickly just convince you that this is true. It's a one-line proof. Okay, so if this happens, then delta h1f is constant. That depends on h1. Okay, yeah. And by the co-cycle equation, if you want, delta h1 plus h2, f at the point x, this is the same as delta h1 f x plus h2, delta h1 h2 f of x, which is the same as ch1 ch2, and this is ch1 plus h2. So this c is a character, and so we can guess. Okay, we guess what this character is supposed to be. So we define the function f of x, which is little f of x times c of x bar, then delta h fx is 1. So this is a constant. Okay? So if I have a constant function, its derivative is trivial, and if I have a linear function, a character, then the second derivative is 0. So it makes sense to define a polynomial. Maybe I will try that. To define a polynomial, f from G to D with disk to be a function of degree smaller than k, or f is a polynomial if delta h1 through delta hk f is trivial for all h1 through hk. And I can do that for any abelian group, not just for FPN. Okay. Right. So examples. So we already have two. So if so the function f is a constant, is a polynomial of degree smaller than 1, or degree 0, and f is a constant times a character, then this is a linear polynomial. And if we take the function f of x to be e to the power of 2 pi I over p q of x, where q is a polynomial. Oh, yeah, so x is x1 through xn. If q is a polynomial, then clearly f of x, polynomial of degree smaller than k, then f of x is a polynomial. Okay, so far so good. What do you want to say? Yes. Right, so polynomials. So here's how we can find the Gowers norm. So if you have f from G to D, then we define the Gowers norm, FUK, to be, well, we average over x1, or x and h1 through hk of the discrete derivatives in directions h1 through hk, f of x. So maybe there is a 2 to the k. Okay, just observe that this is the same as the definition we had before. This is averaging over cubes. Let's just check this for you too. Well, this is the average over delta h1, delta h2 fx, which is f of x plus h1, f of x plus h2, f of x. Kind of a mistake to write it in this direction. Which is exactly the U2 norm. We average over the cubes, two-dimensional cubes. Okay? So here are some very simple observations. So first observation is that if f is a polynomial, of degree smaller than k, then clearly all these derivatives there annihilate, so they're all 1. So the UK norm of f is exactly 1. And vice versa. Okay, since our function takes bounded values, it takes values in the unit disk. If we know that this average on top there is identically 1, then all these derivatives must be 1. So f is a polynomial if and only if this happens. Okay, so this is observation 1. Observation 2, maybe I want to leave this definition. So observation 2 is that if f, say, were to take plus minus 1 values, is a random function, okay, so suppose I were to flip a coin for each value of f, then UK norm of f is little o of 1 with high probability. Okay, so if a random function has small UK norm, so we already saw this before, random function has small UK norm, if the UK norm is 1, its highest value, then the function must be a polynomial. So what is the inverse question? Is what can we say about a function f if we just know that this norm is bounded away from 0? Okay, so again, you can think of it as a sequence of groups growing with n growing. So what can you say about a function f for which this is greater than 0? So maybe one more observation. Maybe I'll leave this guy up as well. If f were to correlate with a polynomial, okay, so suppose you have some function q of degree smaller than k, q. So suppose you know that fq, which is the average over f of x, q of x, if this is large, then applying sufficiently many Cauchy-Schwarz inequalities, you can get that f uk is larger than some constant, depending on delta. So if you correlate with the polynomial, then you get a large UK norm. Okay, so making these two observations, then the inverse, we can try to guess what the answer to the inverse question is. Or is it true that if we know that a function has large UK norm, will it correlate with a polynomial? If it correlates with the polynomial, then definitely yes. And if we already know actually that the answer, so if it depends on the group. right? Because if we take the group to be Z mod NZ, then if you're in Benstock, then the answer is no. So it's not true that it's sufficient to take polynomials over here. So the question is for this group, for fp to the n, is the answer yes? So let me, does f correlate with a polynomial? So we have some information about these average of derivatives. Okay, we know that it's biased away from 0. It's not like a random function, and we're trying to see if we can extract some polynomiality out of the function f. So this is what this says over here. Right. Let's see that. Yeah. Okay. So maybe the first case to examine would be an extreme case. Suppose delta is not equal to 1, but actually very close to 1. What can you say then? So. If delta is very close to 1, then there's a theorem of Lon, Kaufman, Krivulevich. I think if you collaborate with many people, you should at least have a short last name. But Litzin and Wonsi Ron is okay. So there's a theorem that says that if delta is very close to 1, then you're actually close to a polynomial. Okay? So if f uk is close to 1, then so in their context, maybe I should say f was a function from from our group G, fpn, to cp. So this is pth roots of units. Unit. These are pth roots. Then, so if it's close to 1, then f is close, say in L1 norm, to a genuine polynomial. Of the form e to the 2 pi I over p q of x. Q is an fp x. Okay? And the argument is actually kind of neat. Basically says that if your norm is close to 1, then there's actually one unique polynomial that you're supposed to be close to. And if it's unique, then you can try to guess what it is. So how do you guess? Well, you ask your cubic friends. So say k equals 2, and you have you're looking at the U2 norm. So so if f were a linear function. If f were a linear function, then the value at each point x is determined by f of x plus h, f of h1, h2, f bar x1, x plus h1 plus h2. Right, everything cancels out. So f of x, if you know the values at these points, then f of x is determined by that. So what can you do? Well, each point x belongs to many of these cubes. This is x plus h1. Well, conduct a vote. Ask all your cubic friends, ask these guys what your value should be, and vote. And determine your new function q. Q is the vote function. Okay, this turns out to be q, big Q. This turns out to be a polynomial. If delta is close to 1. Okay, you have to have delta sufficiently close to 1 to make this a polynomial. Okay. But this argument can't work if you have delta not close to 1, but just bounded away from 0, because there's no unique choice. There's no good guess that you can have. You can have, if your function f were a sum of these functions, a sum of polynomials, then it would correlate with each one of them. There's no unique guess. Okay, if there's no unique guess, then this strategy can't work. So we're back to this question that disappeared somewhere. Didn't. It's right in front of me. We're back to this question. What can we say if we just know that it's bounded away from 0? Okay. There's too many backwards, and I'm not sure which one to use when. Okay, I'll use this one. So this is the calculation for if k equals 2. If we're looking at the U2 norm, then this calculation, you saw it in Ben's talk and maybe also in Luca's talk. If k equals 2 and f U2 is greater than delta, that implies that f hat, the L infinity norm of the f hat is greater than some constant depending on delta, so maybe delta squared or root delta or some constant depending on delta. This is the same as saying that f correlates with a character. Okay, there is some character that f correlates with, so f correlates with a linear function. Okay, so in this business, things get interesting when you go up. When k equals 2, this is Fourier analysis, and the first interesting case is what can you say if actually wanted that on this one. What can you say? What happens if k equals 3? Okay, this is the first interesting case, and this is a theorem of Green and Tau. If the characteristic is greater than 2, and Alex would. I really hope I'm spelling it right for p equals 2. Am I spelling it right? That this is true. So if let me write exactly what's true. If f u3 is greater than delta, then there exists a polynomial q in fpx such that f correlates with e, right, f of x, 2 pi I over p q of x. Okay, this is actually more quantitative, but let's just write it as a constant depending on delta. Okay, so this looks very, very encouraging. So based on this, it's very natural to try to guess a theorem, or what should happen when you grow up with k. Yeah. Yeah, so you think of n as, yeah. Either think of n as being very large, or otherwise you'd have to take maybe this constant to be smaller to deal with the smaller n's. But yeah.
But some of this c of delta
depends only.
P of delta.
Yeah. So p is fixed. P is fixed. P is fixed for that. I wanted to say that it's 2, but I don't want to say that because I want to talk about higher characteristic as well. So I won't say that it's 2, but for some people it's always 2. So where was I? Yeah. So here's conjecture. So suppose f uk is greater than delta, then there is a polynomial. I didn't write there actually. Should say something about the degree. Degree of q is smaller than 3. Then there's a polynomial Q fpx such that f correlates with e to the 2 pi I over pq greater than c delta, degree smaller than k. Okay, so this is the natural conjecture. We know it for 1, we know it for 2, we know it for 3. So obviously 1, 2, 3, infinity. But the surprise is that it turns out to be false. There's a counterexample. Which is due independently to Green and Tau and Lovitz, Shulam, Samordnitsky. I already spelled it once correctly, so I don't feel obliged to try to do it again. Lovitz, Mishulam, Samordnitsky give a counterexample. So their counterexample, here it is. It's simple to write down. So you look at the symmetric polynomial, S4. It's the sum of xi, xj, xk, xl. And you look at the function. So the counterexample in F2. You look at the function f of x is -1 e to the 2 pi I over 2 s of x. And it turns out that while this function has large U3 norm, okay, I'm using the combinatorics notation and not, so the Ben notation and not the Benji notation. So Benji Weiss used this for something different. Okay, so this is bounded away from 0. But it doesn't correlate with any polynomial of this form. It doesn't correlate and. Thank you. So I just claimed that U3 is okay, then 4. U4 norm is large. U form is large, but f is orthogonal to any cubic polynomial of that form. So f of x and e to the 2 pi I over, or -1 to the power of q of x is little o of 1 for any q in f2 x. So remind you, x is x1 through xn of degree smaller than 4. Smaller than 4. Okay, so kind of bad news, and I think for a while, discouraging news. For a while, people thought that, okay, pack your stuff and go home. But then we discovered that actually this class of polynomials that I left the definition on top on purpose is larger than this class this class of the form -1 or e to the 2 pi I over p q of x. The class of functions satisfying that equation over there is larger, and if we actually allow ourselves to include those functions, all the functions that satisfy that polynomial equation, then this counterexample is no longer a counterexample. So here's an example. So let's let's call these guys, I wanted to leave that as well. So these guys over here, I'll call them classic polynomials. I call them classic polynomials. And these guys satisfying this condition on top, I'll call them non-classic. Non-classic polynomial. So here's an example of a non-classical polynomial. So take e to the power of 2 pi I sum xi over 8, where this just gives you, this is the function from f2 to 0, 1. It just tells you if it's a 0 or a 1. Okay, I don't want to count mod. I don't want to count inside the group. But okay, so this function is a non-classic cubic, and actually, it does correlate with my function. Okay, so actually, this is a non-classic cubic, but it actually so obviously it's not inside that. It's not in this set of classical cubics, but it does correlate with this function. So we're back in business. We just need to modify the conjecture. So it's either that or rewriting it. So instead of writing this thing, I will write Q, where Q satisfies delta H1 through delta HK. Satisfies this condition that I wrote on top of there. So this is a new, slightly modified conjecture, but it can no longer be ruled out by this counterexample. And rightfully so. Where now? Well, let me say what we... Well, this definition should hold... Well, let me write what we know, and then I don't remember what... Well, the people are here. So your examples, examples for all characteristic is when the polynomials are of larger degree than the characteristic. So typically the difference between classical and non-classical polynomials begins when the characteristic is smaller than the degree.
Well, because if k equal to 2, then it's character. You get a condition that is equal to 1, then it's a character.
What are you talking about?
K equal to 2, then it is...
Yeah, so that's exactly what I was saying now. So classical polynomials and non-classical polynomials coincide when the degree is smaller, equal than the characteristic. Okay, so what is it that we actually know? So we can't actually fully prove this yet, although I do believe that this is true. So let me tell you what we do know. I really don't know what to do with these blackboards. Okay, so here is let me see if I forgot something that I wanted to say. I don't think so. So here's what we do know. So this is a theorem. So joint with tau. And it's the following. Okay, so let f be a function from G to the unit disk with f uk greater than delta, then f will generally correlate, f correlates with a polynomial of bounded degree, of degree bounded in terms of p and k only, bounded by. Okay, and well, if the characteristic is high enough, so if p is greater or equal than k, then we can get the correct degree. Then CPK, I guess, is k minus 1. But let me just say something to convince you that of why we do hope that this conjecture is true in full generality. So evidence towards full conjecture is that U4, or the conjecture for U4, is true for all p. So don't go looking for a different counterexample, at least for the case U4. Yeah.
Does it help you if you know that f itself is a polynomial of degree exactly k?
To reduce it one by one. I have to think about it. Well, since I didn't even bother sort of trying to figure out, this comes out computationally out of the proof, but since I strongly believe that the full conjecture is true, then I don't really.
The proof doesn't get any value if f is a polynomial.
Well,
The lowest possible degree, which is not this.
I don't know yet, but well, that's an approach. So if I have time, I can try to explain what's the problem in small characteristic and how can you may be able to attack that using the fact that you already know that you correlate with a bounded polynomial. So that already puts you in a much smaller class of functions that you need to check things for. But anyway, so I want to say what are the ingredients for this theorem. So there are three main ingredients. Okay, first one is correspondence principle. Sorry. Translating this problem to a problem in ergodic theory, which is associated with the counterpart of the Gowers norms in the ergodic theoretic situation. These are, we call these, may have time to describe them later, these are Gowers host Kra norms. Since they were studied by Host and Kra in the connection of a Z action, we're going to look at a different group action. So these are called Gowers host Kra, so I'll call them GHK norms. Okay, so the first step is to a kind of a compactification process. So you want to, instead of looking at the sequence of functions and trying to work with it, then you work with one space, one big group acting on it. So it would be the big group is going to be the direct sum of FP. And you have some associated norms that correspond to look very similar to the Gowers norms, and you need to understand them. You need a structure theorem for them. So this is first step is translation. Second step is a structure theorem. For the GHK norms, and this is joined also with Vitaly Berkelson. This is I guess the main ingredient. And third, so there's one way. First, you need to translate this to a question. So this procedure of translating, taking some combinatorial problem and translating into an ergodic theoretic problem, this I guess was first initiated by Furstenberg in his proof for Semirates theorem. But so this first step over here is a kind of variation on that, but not a very straightforward one, because you need to keep track of these norms, and you need to get a special system, so it has to be ergodic. And in general, the Furstenberg correspondence principle doesn't allow you to do that. And if you work with a z action, you actually can't do that. So it really works to our favor in this case that we're working with this nice torsion group that has lots of generators. So this is the first step. Second step, as I said, this is the main component. This is a structure theorem. And third one is, okay, so we have the structure theorem, we have some theorem in the ergodic context, but we want to pull it back, and that's not trivial as well, because when we lose some we have some error when we go back, and then we can use the delta close to 1 theorem. So third part uses the delta close to 1 theorem. No. Who's asking that? Well, depends on how you want to call it, but not really, because so depend on what you want to say as a correspondence principle. So
I mean, you have 2 papers on the subject.
the first paper is 1 and 3, so it's ingredients of this result. Ingredients of this result is 1, 2, 3. 1 and 3 are done in one paper, and 2 is done in another. Okay, so when you can take your original problem and translate it to a problem having some function in a measure-preserving system, having large Gowers-Holzkreis norms, and ask a question about these systems. What can you say about these systems? Okay, but so you find out that they correlate with a polynomial. I'll describe that in a minute. But then you want to pull this information back. It's not like the Furstenberg correspondence principle, which is very clean, right? So you have this condition is if you have this pattern, then automatically you have it there. So there's work on the way there, and there's work on the way back.
It's just a matter of language. I mean, I think when you talk about the Furstenberg correspondence principle, you refer to the whole process.
Okay, so I think of it as one is the translation, and one is, okay, well, it doesn't matter. Okay, it's the same. It's what you think. Is that okay? Anyway, delta close to 1 theorem, AKK-LR. This is computer science language. Then you need to use this delta close to 1 result. Right. So what I do want to spend time saying more about this structure theorem. And what goes in it, and why might you be happier using ergodic theory than living in your small finite world? So what goes into that? So ingredients of ingredients. what goes into 2? So 1. First thing that goes, so I will describe what these norms are, but first thing that goes is a structure theorem of Furstenberg-Zimmer. Structure theorem. That essentially, this helps us, this is a first kind of structure reduction that we get. So we can first, essentially allows us to reduce from the case of general measure preserving systems. I'll describe what this object is in a minute. But from general measure preserving systems to very special ones. So special ones, or ones that are built out of finite, or are built out of a finite number of isometric extensions, whatever that is. But won't say that. But there's a first there's a first structure theorem that already allows one to reduce to relatively structured relatively structured measure period system. I'm not going to say anything about this. It's not easy. Second part is a cubic construction. Which essentially is due to Host and Kra in the case of a Z action, but can actually be made very general, even outside our situation. I'll describe that. But what the essence of this, what this allows one to do is well, this is at least what I'll try to show, is that this gives two equivalent definitions for polynomials. They coincide if you're sitting inside fp to the n, and you think of that as a measure-preserving system with a uniform measure, and you act with your group acting on yourself. So they coincide in this case, but in general they don't coincide. So this gives you two alternative definitions of polynomials. Also shows you how polynomials can be defined very naturally in measure-preserving systems. So this is number 2, and the third part is the key, I guess, technical difficulty, or the heart of 2. So 2 is the heart of 1, and 3 is the heart of 2. No, that didn't quite work. No, not quite. Well, I wanted to have 3 on the same one, so I'll have it halfway. No, it's not going to work either. So 3 is going to move to another place. Let me write 3 there so I can use this for the construction. 3 is solving a functional equation. This is sort of the key difficulty. Somehow the Z strategies don't don't work for this. Maybe I'll be able to describe what this equation comes from. So yeah, so I promised I want to describe this cubic construction, or in general how, or maybe before that. So what is, I don't know why I take this around. What is a polynomial? Well, how can we define a polynomial in a measure-preserving system? What is a measure-preserving system? What is a polynomial? So here's what is a measure-preserving system? So you have some phase space X. So you have some probability measure space, probability space, and you have an action of some group. In our case, we'll be looking at so G now changes its role, but it's, if you allow n to be infinity, then that's fine. G fp infinity, or direct sum of fp. So we look at the action of this group, and what does it say that this action, this is a measure-preserving system. This just tells you that these elements preserve the measure. So if you take any set A or B inside B, then the measure of TGB is the same as the measure of B. Okay, so this is measure-preserving system, and we also need to assume that it's ergodic. This tells us that if TGFX, which is short notation for f of TGX, this is how TG acts on functions, is f of x almost everywhere for all g, then f is constant almost everywhere. No constant invariant functions. Okay? So how do we define a polynomial? Well, we can imitate what we did in the finite case. Okay, so we had this discrete derivative. There we differentiated with a group element. We can also differentiate here using our group elements. So here's one optional. Okay, so what is a derivative? Well, you can define the derivative in direction g of a function f. Same. Just now we act with the element g on x. Okay, if G were acting on itself, and if my group was the finite field, then this would just be x plus G. Okay, so this is the derivative, so here's one. Okay, so first observation: if delta G fx is 1 for all G, almost every x. Well, this is the same as saying that f is Tg invariant, right? This is the same as saying that f of Tgx is the same as f of x. By ergodicity, this is why we need the ergodicity assumption. By ergodicity, this means that my function is constant, right? Then f Tgx is f of x, almost every x, all G, and ergodicity implies that f is constant. Okay, so we have where to stand. So if we have that, then of course our next step is to define. So here's a natural definition of a polynomial. So here's a polynomial. So this is definition 1. Polynomial say that f from x, so this is a measurable function from s to the unit disk is a polynomial of degree smaller than k if delta h1, delta hk, f of x is equal to 1 almost every x, all k tuples in G. Okay, so here is one very natural definition of polynomial, and this one.
The new definition, it was never there in your.
Well, so let's see what happens for k. Well, it wasn't called this way, but so let me tell you what it was called. So what is delta hf? What if you know that this is 1? Okay, this is second one. First derivative means it's constant. We already said. What can you say if the second derivative? Then it turns out, well, same calculation as the one, very similar calculation to the one we did before. Then f is an eigenfunction.
Is this related to the generalized repeated eigenfunction?
That's exactly what I was going to say. So these guys were called, or are still called, generalized eigenfunctions, or maybe generalized eigenfunctions is used for also other things. It's not only one-dimensional. So they were really called k-step or k-step eigenfunctions. So f is an eigenfunction. This is the same as saying that f of tgx is some lambda depending on g f of x for every g. This is an eigenfunction. So if you have many of these, so you can call them k-order eigenfunctions. So a polynomial is like previous definition of what you would call it a step k eigenfunction or k-order eigenfunction or something like that, smaller than k-order eigenfunction. But okay, so this is option 1. But let me describe a different way to okay. Oh well. I have until 12:30. Did I start at 12:15 or? Okay, good. So here's this is a kind of a general construction of you can define in general what a cubic complex is, okay. So what is a cubic complex? This is a very natural way for polynomials to come from. So what is a cubic complex? Well, it's a sequence of sets. xk, so xk. So I want more board space. So I will, don't know what to do. Never mind. Okay, so I have xk coming to xk minus 1. So I have a sequence of sets. So I think of these guys over here as k-dimensional cubes. And from a k-dimensional cube, I don't have only one map to the previous set, but actually 2 k maps. Okay, so I have all the boundary maps. So these are sets with maps that are called boundary maps. So I have delta 1 plus minus through delta. I'll make this real very soon. Okay, delta k plus minus. So you can think of it, here's a cube. And each point can go to kind of the face maps. Okay, so you can go to your respective faces, and from each point here you can go to your your lower dimensional cube. So these are very nice objects. They have very nice symmetry properties because of these 2k maps and the symmetry between the faces. So if you have this object, so I'll erase this. And you have these boundary maps, then down here you have maybe your original set, x0, x1. Then you have these maps going in the other direction, dual maps, that come from functions, measurable functions from x0 to s1 to so each one going up, so this is measurable functions from xk to S1. So you have these dual maps going in the other way. So if you start out with a function on the lower step, and you take this dual map, I don't want to define it, but you can think of it. You can define it using, so you start out with a function here, you want to define a function on the next step. This will be some kind of average involving the projections onto the faces. Okay, so if you have this construction, you have this dual construction, and so if you take a function here, so think of this as your original set, this is what you were interested in. You have a function here, if you apply this map k times, iterate this k times, so if you start with a function f from x0, say to the unit circle, then dkf, after applying it k times, is a new function from xk, from xk to the unit circle. Okay? And this is kind of a general term associated with cubic complexes, that you say that f from x0, say to S1, is of finite type smaller than k if dkf is 1. Okay, this is very general construction, and many polynomials in many situations arise from this type of construction. So, question is, can you design a construction for these measure-preserving systems that will give rise to these polynomials that sit over here? This is the construction that Hosse and Kra did for z actions. It's always a problem if you have too many choices. So who are going to be my xk? So xk is, well, I take x to the 2 to the k. Okay, I take, beginning is simple. So b to the 2 to the k, the tensor algebra. I take the diagonal action t tensor tg 2 to the k. So this is k 2 to the k coordinates, and I act with the same map on each coordinate, it's a diagonal action. Okay? So the secret is always in the measure. So I don't know if I'll describe the measure, but I can say something about it. So mu k, well, one obvious choice for a measure is just to take the product measure. But that doesn't work. It doesn't gives nada, gives nothing. Okay? So if you take the product measure, you get nothing. But if you take a measure that is constructed in a kind of a natural way via some UK, I'll write it, but this is, if you haven't seen this, then this is not going to help you, is a joining, self-joining of uk minus 1 over t 2 to the k minus 1 invariant functions. Okay, so in general, this action is not going to be an ergodic action. Okay, so you're going to have some invariant functions. Forget what this is for a minute. I just wanted to tell you that it gives something different. So use this construction. This is, and I have to tell you who the boundary maps here, but this is easy boundary maps. So you just project onto the faces as they come from the cube over here. So here is, for example, if you're looking at x2, so this corresponds to x to the 4th, and tensor b4, and t cross t cross t cross t, and some measure m2, or if you want m, I don't know, do you want mk? Okay, m2. Then if you have x0, 0, x0, 1, x1, 0, x1, 1, so a boundary map, say delta 1 plus, we'll take this to x1, 0, x1, 1, and delta 1 minus, we'll take this to x0, 0, x0, 1, and delta 2 will look at these guys, and delta plus and minus will look at these guys. Okay, so I have four boundary maps. okay, so this is a construction, and it turns out that if you look at this construction, then finite type functions coming from over there are exactly those polynomials that we define here. And, okay, so punchline. Okay, I don't know where to go. Okay, punchline. That f is a polynomial in sense 1 if and only if dkf is 0 uk almost surely. Okay, and this is as I said, if you start out with x being this fp to the n, this finite group, then these two definitions, they coincide. But they're genuinely different. So you can think of this as one equation encoding all this information about all these derivatives in all these directions, gi. Okay, so this is a characterization that is extremely convenient. And let me finish by just saying what is step 3? What does one need to solve? Who is? Where is, yeah, depends. So, yeah. So you can move from additive or multiplicative as long as, what? It's always 2, but, okay. So the same, so I said that there's these map xk minus 1, x1, x0, and these give rise to these maps. These are boundaries. But you can look not only on functions, but you can also look at cocycles. So from G cross. So what is a cocycle? Let's say any y. This would be a function that would satisfy f of g plus h. Y is the same. It's very dissimilar to that equation we had at the beginning of the talk. F of fg of th acting on y, fhy. So you can have these maps going from these cocycles as well, all the way up. Okay, and what you really need to, this gives you cocycles with respect to the action, the diagonal action in each one of these cases over here. So what you need to solve in punchline, or well, I don't know, main equation, second punchline. What you really need to solve is, suppose you, I'll write it, board. And with this, I'll finish. Suppose you have a function f, so a cocycle, so that its kth derivative, in this sense, it's dkf, is a coboundary. Okay. So again, if you haven't seen this, it's not going to help you, but if you have a notion of cocycle, then you have a notion of a coboundary. Then f, there's a function g bad, q, which is cohomologous to f. Okay, so 1 or 0 depending on where you live, if you're multiplicative or trivial. Okay, there's a function q cohomologous to f such that it's a true polynomial, dkq is truly equal to 1. So it's a polynomial. Okay? So this is sort of the main thing you need to understand. But okay, I think I shocked you, and I'll stop.
Is the structure theorem too complicated to state?
What structure theorem?
The one of which this was the 3 steps of the group.
No. I didn't state it. That's true. Okay. Step 2 of 1? Of ingredient 1?
Yes.
Well, it's not difficult to state, but I just didn't define what the GHK norms are. So structure theorem, if I have this system, this is an ergodic system, okay? So ergodic. And if I have f uk x, okay? Very similar, and if you look at it, it almost looks the same. There's just this limiting process that you need to take. But very similar. If this is greater than delta, then there exists a polynomial q such that fq, in this respect, this is the integral over fq bar d mu, is greater than some constant, depending on delta.
Is the degree bound on?
Sure. Well, degree is associated with.
Where do you lose?
Why is there a degree problem?
In where? Yeah.
It's difficult to show. It's inside this problem over here. But it's the main problem somehow is that when you try to if you take a polynomial and you want to find a root of it, okay, some polynomial whose pth power is this polynomial, you lose degree. Okay, so you can't find a polynomial of the same degree, so you lose degree. Now, if you're in the finite world, you lose exactly the right degree. That's why there is hope to actually get it for low characteristic. But if you're in the ergodic world, you can lose too much. Only happens in you lose. So basically, the point is that if you take a polynomial q and you take it to the power of p, then this is a polynomial of degree deg q minus, you lose p minus 1. Okay, and other direction as well. So if you integrate in the finite world, this is the same. If you lose enough, so if your characteristic is large enough, then you always end up with a constant. And taking roots of constant, that's kind of the issue. You don't. It's more difficult to explain. It's a technical issue, but the problem is in this. Okay, so the problem is in this degree loss when you take pth root or of a polynomial. And if the characteristic is large enough, then the polynomials you deal with are always of low enough degree that you lose everything. Okay, so when you take a degree p, then you get a constant. I'm not making any sense, am I? Maybe I can try. Maybe I can try to explain it more in detail later. But it's a technical issue due to this fact, due to the fact that taking roots increases degree. And well, otherwise these definitions are not equivalent. And
Why do you have equal density in this case?
that's the trick in the correspondence principle. Because you have so many generators to handle, you can shuffle them around, and you can't. So if you were trying to do this for a z action, you'd get stuck. So you can get this kind of correspondence principle for a z infinity action. You can do the same, and maybe get. I think you could probably get in there. So you could ask, what if I want to apply this strategy to try to get the inverse theorem for z mod nz? Well, problem is that first of all, okay, there's this problem that you need a theorem for z infinity. But say you fix that. The moving back is also not a problem because there's no nice criterion, right? Polynomials, their derivative is 1, but bracket polynomials.
You started with p small and n large, and then Tau's theorem, Tau Z theorem said if P is bigger than equal to K, then
Yeah, this is if P. So we don't have this. If this is the characteristic problem. If the degree is smaller than the characteristic, then we never have this root problem. It only surfaces up when the degree is greater than the characteristic, and due to this loss, right? This is small. This is going to be 0, usually. Okay, so when it's 0, I'm happy. When it's no 0, I don't know. I'm in trouble. Okay, so.
and also the characteristic doesn't affect the Frobenius. That is, you don't need Hasse derivative.
I don't know what these are.
P times,
So
you take P power, P times something, the derivative in classical.
if I take P power, then I do use what I know of the characteristics. I use this fact that when I take a P power, my degree decreases by exactly this. Yeah, I use that. I do need that. Yeah.